Okay, so the next topic, so the beginning of the course that we want to start this is using this this group ZP, which is the kind of basic notion that we want to start this. So the kind of heuristically speaking, the problem that we'd like to talk here is that you take these p elements, so let's say 0, 1, 2 until p minus 1, with b being the some natural number and p at least 2. And what we want to do is that we want to think about these points are kind of like on a circle. So we draw a circle. Oh, that's not really a circle. Let's draw another one. Maybe this is, yeah. And we put them like around here. Let's say put 0 here, 1, 2, 3, 4. Let's say this is now the 5. 5. This would be like p equals. In this case, it would be 6. And in order to think about them as points in the circle, we need to really like identify somehow some type of group structure within these points. So what you could think about here is this example. I have it on the lecture notes, which is I talk about this like passenger broccoli. And these things, and what I'd like to think about as example is you start from let's say the point at 0, that you have some this could be like a round table of, let's say in this case 6 people, and then one person at the 0th position has a piece of broccoli on his hand. And wants to, or maybe a bowl of broccoli, and wants to pass it to the one on the right or on the left, sitting next to them. So it could be like with probability, let's say probability half, you're passing it on the right, or with probability half, you pass it on to left of you. So there's like possibilities for going both directions with this notion, and. Once it's here, like it's given to, let's say, with probability half, it's given to the person sitting at the position 1, what they can do now is to then pass it on to the next one. So they could pass it with probability half to this one, and then with probability half back to the original person. That could be also possible. And it can continue like this, that then, let's say it went to this person over here, then it can again, like you can pass it on with probability half back to here onto another thing. So you end up to this kind of an initial state that you start to like randomly pass on to this item to people around the table. And what you can then ask are like questions like what is the probability, for example, that the person sitting at the position 4 gets it, and how many steps does it take for that person to get it? Like what is the expected number of steps that it takes for that broccoli to reach that person? Is it possible to avoid something like this? Is it like unavoidable, or what's the kind of thing that you could like ask from this, from this? And what you can think about this problem as like a group. So you take these points. And you take this, you define the ZP as follows. So you take ZP to basically be this set 0, 1, 2, p minus 1, and you put here a group element. So you put this kind of group action, which I think in the notes I use this notation circled plus to make it like happen. And so what we do here is that we define this as 2 points. So if you think about it, let's just draw the circle again here, just for the sake of it, that you see the kind of idea. So we have, let's say, this 6 points here, over here. Okay, this is not very. Let's put it on these points. So we have the 0, 1, 2, 3, 4, 5. And what we want to define is that basically an operation that when we move to the right or move to the left, so we want to like basically have this idea that you move back and forth with this idea. And so what we can do is we can define, let's say, if we take a t in this 0, 1, p minus 1, and we take an s in the same set, p minus 1. So that would be like, let's say, this would be your t, and then let's say this would be your s, for example. And then you want to define their, let's say, addition, so t plus s. And we want to just them to be basically that there's nothing mysterious. So it's basically just we just add these numbers together. But the problem here is that if you add these two numbers together, look, in this case it's fine. You have this would be here. This would be 3 plus 1. So you could define this to be just this is 3 plus 1, which is 4. This would be fine. But then the problem is that you want this outcome to be basically in the circle. So what we also define this to be t plus 1 and then minus p, and we have two conditions. So basically when we should use either one of these. So the first one is of course when t plus s is less than p minus 1. So whether it's between these numbers, the outcome that you obtain, or the other option when t plus s is at least p. So that's the kind of the last condition. So that's the basic idea, that once you add these together, then you end up to this operation. And now, heuristically speaking, what you can do here is that you can take, let's say, the position 1, and then you can add maybe 3 times. You can maybe go like, you can then make an intuition that if you start from, let's say, t is equal to 1 and s is equal to 3, sorry, the other way around, maybe 3 and s equal to 1, and then that means that 3 plus 1 means that move 1 to the right, like kind of like right of 3. So that's kind of like what you do in the circle. So you move around, and then in the same way, you could define t minus s to be in the same way. You could just define this to be the in the same way when this is become. But you could actually, if you want to, really, this is just t minus s modulo p that you could define, because the t plus s that we use the notation here is just t plus s modulo p. That's the definition what we are using basically here. So in the same way, then you have this negative notation over here that basically means that you're moving s positions to the left of the circle. So when you start from here, let's say you wanted to move to the right, that's like moving to the left, so you get right. So that's plus 1, and then this is minus 1, for example. So this is the group. That's the whole setting of the course. So there's not really much to talk about this actually, because this is quite simple. You will see that we have this theorem 2.3 on the notes that says that this ZP and with this operation is a group. It's actually an abelian group, but it's a group. So it satisfies this that if T and S belong to ZP, this is like well defined. This belongs to T plus S belongs to ZP. And then you have the T plus S plus R, this kind of associativity, T plus S plus R, and you can change the order. And you have the identity element, the 0 here will be the identity element, so it will satisfy this T equals T plus 0 equals T for any T in ZP. And then what you have, this is for me, T, S, R, and ZP. And then finally you have this inverse elements that for any T in ZP, there exists minus T in ZP such that T plus minus T is minus T plus T is equal to 0. So that's the kind of like a minus, formally the minus element. You can basically define it by this, that it's mod p is then minus t plus p equals p minus t. So that's the formally the inverse element, what you could define this this number to be. Be in the circle. So once you go into the group, you could define it as a point in the circle. And it's also like an abelian group, that it's this is very important actually in the kind of theory. Is an abelian group because a lot of the kind of like, for example, the symmetric group that we talk about in the card shuffling, that's not an abelian group. It's not commutative. So it doesn't satisfy this property that we have for this group. So that's one of the reasons we want to really consider this is this as commutativity relation that we have for this group. Okay, so I don't know. I hope you got like some kind of a feeling about this element. So. There's some other things I want to maybe talk about, some kind of basic things we have about the group. So there's more things in the lecture notes, and examples of, like, for example, how do you find examples of like inverses, for example, of points. There's a couple of examples that I have written, like maybe like, for example, just very quick, if you want, if you take in like Z3, for example, we have the following that, well, actually, let's put Z4. This is in the example 2.5, that in Z4 we have the 2 plus 2. If you take these elements, you get 2 plus 2 minus 4, because that's by the definition, so you end up actually into 0. So so the inverse of 2 is 2 in Z4. Just to like give you like a little bit of like feeling that when you consider the group of 4 elements, for example, it really depends on what group you are in. So for example, if you have the point 0, 1, 2, 3, and you have the point 2, and then you try to find the inverse of this, which satisfies this property that 2 plus 2 is here, then it's really 2 itself. So that's the one that the inverse of itself. But in, let's say, in Z3, you would have a different situation, that in Z3 the 2 plus 2 would be 2 plus 2 minus 3, which is 1. So that wouldn't be true in this kind of situation. That's the kind of the main thing that you must see in this example. Okay, so the other thing that will be like very important in the kind of theory that we will see is will also be like subgroups. So when we have a group like this, so for example ZP, we also like want to like really think about what are the possible subgroups of these elements. They will be important in the theory of random walks, because it kind of really depends on the structure of the group itself, whether, for example, your random walk is getting stuck inside like a subgroup, for example. So let me talk about a little bit about subgroups. So what we have here is, let's say we take this group Z4, for example, and now we have this circle, and we have these 4 points in the circle, 0, 1, 2, and 3. Then what turns out that there is this specific part of this group which is taking this subset. So if you take this subset, let's call it gamma, which is 0, 2, which is a subset of Z4, then this is a subgroup. Because what happens to it, that it's also a group, it is also a group, and it's basically like closed in the sense that it's if you have the 2 points inside the set that you stuck in here. So for example, just if you want to see it, so if you take 0 and let's say 0 plus 2 or 2 plus 0 and 0 plus 0 and 2 plus 2, you get this is 2, this is 2, this is 0, and then this is, remember, like we did earlier, it was actually 0. So these all are back in here. So it doesn't like escape. So when any kind of operations that you apply to these elements inside the subgroup will remain inside the same space. So that will be like kind of important, that if your random walk somehow, we will later see in the course that if it somehow gets stuck between these 2 points, it gets like concentrating into these kind of subgroups, then that might be an obstacle for your kind of mixing of the random walk, the kind of things that you'd like to talk about, whether your process becomes unstructured, like we will talk about in the card shuffling, that whether your deck of cards becomes random enough, then these still will be types of obstacles that you might see later on, that this concentration on subgroups, which will be difficult. And that's kind of like we will later see the harmonic analysis tools will allow us to deal with these problems. But subgroups are like basically the kind of one of the main tools that we want to understand the kind of random walks later on. And one notation that I use in the course, this is like important, is this notation that if you take like a subset of this set B, then we write this A as the subgroup generated by A. So basically this is the gamma. You could define it many ways. In the lecture notes I use this one of the definitions, just using all the possible elements, but basically this is the smallest subgroup of set B containing this set A. So for example, maybe like a simple example is that if in Z4 the subgroup generated by 0 and 2, this thing that it's just itself, because it's we knew that this was already the subgroup. But then, for example, if you take, I think if you take 0 and 1 and 2, I think the only thing that you get is Z4, the best generation that you have. And then, of course, like if you take something like trivial like this is just itself. And there's also, like, of course, like the other generators that you could have if you have a group. You could actually generate your group with a single element. That's like the kind of the characteristic property that you could have this. So, for example, there is this maybe theorem that you could like look. This is not proven in the notes, but this, for example, is that this theorem 2.9 on the notes that says the following: that if P is a prime number, it's like a connection to a little bit to number theory. That if P is a prime number, then ZP only has trivial subgroups, which is the 0 and ZP. So there's actually no other subgroups. There's only these two trivial ones in the prime number case. That's because of the divisibility properties. You could try to look at it yourself a bit if you want. It's not examinable what we want in this course, but you can, like, it's an interesting like application of like basic modular arithmetics. And the second thing is, of course, that if P is not prime, then all subgroups of ZP are the following. They are zero, this of course, the trivial ones, ZP, and and then just the subgroups generated by a single element. So basically these subgroups, if you use this notation, this is generated by single elements for all t in ZP that divide P. So there will be like many elements in there, but of course the ones that divide this specific number. So that's why in the prime case you don't have any of these. The only options are just these two. But when you don't have a prime, then you also have the subgroups that are generated by a single element. This is just something that you might have seen already in basic group theory, but you could just like a feeling for you what the structure of the ZP is. It's very simple. It's an abelian group. It has very trivial type of subgroups and everything, and that's the kind of group theoretic structure of the setting we want to start from. Okay, so in the next topics I will plan to go into the probability theory in this subgroup.